Welcome to this session of invited talks. It's a big pleasure for me to introduce Karin Tornberg. Karin is professor in numerical analysis at KTH in Stockholm. She works mostly on numerical algorithms for solving PDEs in dynamic geometries, with applications mainly to multi-phase flows. She was invited speaker at the ICM in Rio in 2018, plenary speaker at the ECN Congress in Valencia in 2019. She has had a number of prizes. I am not going to list them just to be a little bit short, but let me just say that she is elected member of the Royal Swedish Academies of Sciences and of Engineering. Today, Karin is going to talk about quadrature error estimates for layer potentials evaluated near curved surfaces in 3 dimensions. Karin, the floor is yours.
Thank you very much. So I'm going to share my screen. It's going to take just a moment to set it up. I'm sharing. Oops. Sorry, it seems to take a while. It was fast when we did it, but now it was slower. Okay, let's see. Oops. Here we have it.
Yeah, great.
Okay.
Yeah, you can go ahead.
Okay, great. So I'm just rearranging my windows here so I can see. Okay, thank you very much for that very nice introduction. And it's a pleasure to be here, or how should I say it? It's a pleasure to have the chance to give this talk, even if I would have preferred to be on site, of course. That would have been wonderful. So this is a long title of my talk today, and I will soon explain it. This is work done jointly with Ludwig af Klintberg and Chiara Sorgentone. In the title, I think we understand the word quadrature error, maybe what we get an error when we numerically approximate an integral. And we're going to try to estimate such errors for layer potentials. And I will tell you what that is, and also why we say that it's important that it's near a surface. So when we use integral equations to find the solution to PDE, which Maria mentioned in her introduction, I've been working on, for example, Stokes flow with drops, viscous drops interacting and so. Then we have to evaluate so-called layer potentials. They involve the Green's function of the PDE. And when we want to evaluate the layer potential close to the boundary of a solution domain, then, sorry, I'm going to take this off. Then it gets nearly singular, the integral. So this is a layer potential in generic form. So if we're integrating over y, then if this point x will be close to the surface or the curve that we're integrating over, we'll get the peak in the integrand, and we'll get something that's hard to resolve numerically. And so we care. Why do we care about this? Well, we can, when we want to evaluate, of course, you always want to evaluate also close to the boundary. You want to evaluate the solution all over the solution domain. And if you want to know when your regular quadrature, the way you have discretized, is good enough, and you can switch to a different method if it's not, but those methods, usually we call them just special quadrature methods, which can be of different kinds, but they all cost more. It's costly to change to these other methods. So you want to know when you actually have to do it. So there hasn't really been any such estimates available. So this is why we've been working on this. So I'm getting back to this generic form later, so you will see it again. But I want to start, before I give an outline and everything, I want to just start with an example, which is the interior Laplace problem. So what you see here is a layer potential. So this is the harmonic double layer potential. So that's the Green's function of in 2D of Laplace equation, and we're differentiating it. So this will give you the solution in the domain. You can evaluate for any point as soon as you know your density mu, the layer density mu. And to find that, you have to we will take the limit to the boundary so that we get an integral equation for mu. And then on the boundary, you can solve for mu. So this is like a two-step procedure. You would solve an integral equation on the boundary to get mu. And once you know mu, you can evaluate the solution at any point in the domain for any x. So this will be the two-step procedure. So if we take that log term that we have and actually perform the differentiation, the layer potential that we have looks like this. And it's actually quite common when in 2 dimensions to rewrite it with complex variables. So I'm going to do that here. So it takes a little bit of convincing understanding that the normal vector of a curve can be related to simply to the parameterization of the curve in 2D. You're really using 2D here. But you can write it on an equivalent form in complex variables that is like this. And this is how it will come out if you think about tau being, there's a parameterization tau of t. So t is a parameterized variable. I will use this notation now that I show some slides to come, but then we will work much more with this when we actually look at the estimates. So as I said, we have to solve for mu. So I want to give you an example. So then we will have to solve for mu. And I'm not going to say much about what we do it, except that we have to, of course, discretize this equation. So what we're doing here is we're going to split our curve into panels or segments. And on each panel or segment, we're going to use a Gauss-Legendre quadrature rule. So this is an example of distribution of 16 points over a panel. And then we can solve for mu. As I said, I'm not saying much about that. We're just saying, okay, we can solve for mu. And once we have solved for this, then we can evaluate this layer potential to get the solution anywhere in the domain. And this mu now, of course, we have to discretize this and we will use the same quadrature rule. So we have mu in the points where we need. So it's still an integral over the curve, but the evaluation point, the z, is inside the domain. So we're going to look at the error here. We're not interested so much in the solution here. It's not that exciting, but we're interested in the error. So what we see here, the error here is logarithmic. So this means that when it's really blue here, we have 15 digits of accuracy away from the boundary, which means that our mu is really well resolved. It's not the problem of the density. So when we're far away from the boundary, we have a small error. But as we approach the boundary, zooming in there, you can see that the error rapidly increases. As c gets close to the boundary, you will have, for a range of tau here, you'll have a peak in your integrand, right? You'll have a nearly singular integrand peaking, and it's hard to resolve it. And you can really see this error increasing. And so the question is, can we understand it better? Can we estimate this error? So here we have I wanted to give just an even simpler example, a 1D example. So let's say that we have this kind of integrand, 1 over x squared plus delta squared. Here we can get a more visual picture of the integrand. So if we plot f of x for a specific delta, we can see this peak. And we can understand that if we take delta to be even smaller, it's going to be even harder to resolve it. And if we plot the error versus delta squared, we see that as long as this is rather large, we have, even with 16 points, we might have 12, 14 digits accuracy, but as it gets smaller, the error gets large. It gets more and more peaked, hard to resolve, the error grows. And of course, then we think, okay, but we know something about Gauss-Legendre quadrature rule. That's a classical one. We can pick out the error estimates that we have and see what it tells us. But if we do in this case, so we pick out the error estimate, we take the derivatives, we get an estimate that tells us that's really overestimating the error. It even tells us that if delta is smaller than 1/2, as we increase n being the number of points in the Gauss-Legendre rule, so we had 16, maybe we do 32, it's telling us that the error actually will increase if we take more points. But the actual error will actually decrease exponentially with n. So we see we cannot use this. Of course, there are other estimates for the Gauss-Legendre, but this really tells us that we kind of have to think more about this specific kind of integrals and seek a solution elsewhere. So we've seen 2 examples so far. One is the 1D example. that I did, and we can write that. That's a of this kind where we can write it on this form. And the 2D example we had was an example of a typical layer potential where we had something in this form with p equal to 1 though, and up here too. But what we see in both of these are that these are integrals which have a pole in the complex plane. So for z naught, some c naught being a plus ib, we have a pole. So not on the curve, c naught is not sitting on the curve, but we have it somewhere out in the complex plane. And this will come back here. Oops, sorry. So the outline of what I will do now is that I will first start by briefly introducing a theory by Donaldson and Elliott for estimation of quadrature errors using complex analysis. And then I'm going to describe how we derive error estimates. And we do that for Gauss-Legendre and trapezoidal rule. And we're going to look at results on the way, kind of building up. I'm going to show first the complex form and come back to the example of the Laplace equation. Then I'm going to, I wrote Cartesian here, but I mean real valued. So on this form, when we stay with the layer potential of this form, I'm going to look at the errors for one-dimensional curves in 2D, which is then of course very related to this. But the reason we go to this form is to also generalize it to 3D. And then we're going to go to surfaces, so two-dimensional surfaces. So the curve in 3D could be the red curve marked on the torus, and the surface could be this kind of squished torus that we would look at, okay? And so there are some earlier results that are very important. So Elliott, I'm sorry for the misspelling, I think Elliott should be with 2T at the end. Elliott, Johnston, and Johnston, they derived an error estimate for this integral. So for this simplest form of that integral, they derived an error estimate for the Gauss-Legendre rule. And they also looked at going up one dimension and having a double integral, and then for two different values of p, the second with a specific a, they also derived an error estimate here. So when we have worked on this, we have had great use of the techniques that they introduced in these papers, and we have derived our error estimates in a sequence of papers. The first steps we took in the paper that was published in 2017, that was with Ludwig. And then as we did some refinements in 2018, we also designed an adaptive quadrature that would keep a certain tolerance in 2D that would guarantee that. But this was, I will get to these generalizations. But then it was more recently that we actually managed to extend this to surfaces in 3D. So those are the most recent parts that we have done. Okay, so let us introduce a base interval. I will call it E because then it doesn't matter. We will, for Gauss-Legendre, that would mean -1 to 1. For trapezoidal rule, it would be 0 to 2 pi. An integral of a function, we just denoted by an I, the quadrature rule by Q sub n, meaning we have n quadrature nodes, TL, we have some quadrature weights. So this is our discretization of the integral. And the error naturally will then be the difference of the two. And one can actually show, and this is what Donaldson and Elliott did, one can show that this error can actually be written is equal to a contour integral in the complex plane, enclosing this base interval. So the Kn here is dependence on the quadrature rule. So it will of course be different depending on which discretization we used, but there is such a function. So to write it like this, we have assumed that we put our contour so that the G is analytic on and within the contour. Now, if we have a meromorphic function so that we have certain poles, so it's analytic everywhere except at some points, then we can write this as a contour and then some residues here. And this C now is a large contour. So if this G is analytic except for this, if it's meromorphic, then we can take this to infinity. So it's really the residues that will give us the dominant contribution to the quadrature error. So these quadrature functions or quadrature error functions, I'm not sure what to call them, these Kn of Z that depends on this explicit quadrature rule, they look different for the two cases. So here is for the Gauss-Legendre one. There is no closed formula, but you have as asymptotically, as n gets large, we have a form for it. And I'll get back more to this rho C function, which is a little bit hard to understand how it actually looks. And then for the endpoint trapezoidal rule, you instead have another, then we have a closed form for this Kn of C. So from these, we actually, so these were in the literature, we have them in Trefet, and this was also in Donaldson and Elliott. And from this, we derive approximate formulas for derivatives of Kn of C. Here it's simple, here it's more complicated. So we can't retain all terms. We retain sufficiently, so to get good estimates. Okay, so for a layer potential on complex form, the integrand would look like this. So this, the Laplace one, as you will maybe not remember, but we'll see, we can put on this, it is on this form. And we want to estimate the error in the numerical approximation. So just the integral and the difference between the integral and the quadrature rule. And using these residue calculus, we can actually derive the following estimate, that it has to fulfill, this is one estimate then. It's not an identity, we're looking for practical estimates that we can use. So we say that the error is approximately equal to this expression here, where now I've left, so far, I've still left Kn in there. It's p minus 1 derivatives of Kn, p sits here, right? And there's one important other factor here that I will come back to. So I've introduced the T0. So my evaluation point was C0. And now I said that T0 is such that gamma of T0 is equal to Z0. So we will get back to that because that one is important. But if we first look at what the expressions become, we just insert our expressions for these derivatives of the Kn. And then we have it for Gauss-Legendre up here and trapezoidal rule up here. So it's a bit hard to digest what these mean. So to make it simpler, we're going to scale off some things and start with the simplest case and then kind of come back to the full case. So if we look at just the simplest integral of this kind, which would be just 1 over t minus t naught to the p, which just means that we're integrating over one flat panel like this with some evaluation point t0. And we want to know that. So then the error estimate becomes this. So this will be the error estimate. And this is actually how we started when we did this in 2017. Now it's just a special case of what we have, but then this is what we started with. So we have this estimate. And so what does it mean? So this rho function here, so for p is equal to 1, this term goes away. So it's all proportional to this. So if we look at p is equal to 1, then the error will be constant on when the rho is constant. And that means that the error is kind of constant on Bernstein ellipses. They are called Bernstein ellipses. So this is, if you have the panel here in the middle and you look at error contours, this is how they will look. This is how your error will decay as you move away from the panel. If you had the trapezoidal rule, you'd have the corresponding result here. And this one is easier to understand. Then it's just the imaginary part of T0, which will be the distance to the real line. And that would give you the decay rate together with n. N is always going to be the number of points in the quadrature rule, okay? So it's decaying exponentially in the number of points with the rate determined on how far or how close you are to the curve, to the line. In this case, it's only a straight line. So if we look at our 1D example, this does not directly apply the theorem, but we had a theorem for this kind in this paper as well. Then if we take out what for our specific function with a0 and b is equal to delta, we're on this form. If we take out the error estimate for this with n is equal to 16, that's the 2n plus 1 being 33 here, then we get this form. And if we plot the measured error and the error estimates in the same plot, we see that we get with this a very good estimate for the error in this 1D case. So this is of course the simplest case, but we get a very good estimate. So that was kind of the base case, the 1D case you can think of as a flat panel. Now we want to do curved panels. So we still keep G, the function, equal to 1, but we want to think about evaluating terms on this form over curved panels. So we have a curved panel here. And what we can see from our error estimate, if we look at it, is that the estimate for a curved panel relates to the estimate of a flat panel, such that we need to evaluate it at this T0. And then there is a shape function here that comes from the parametrization of the curve. Now, if P is equal to 1, it doesn't enter. Well, so this T0 is the pre-image of C. So if we think about, we have a parameterization and we do an analytic continuation of it, then our T0 is the point that would under gamma would map to Z0. And of course, if we have C0, we'd have to go the other way to find our T0. Sometimes you might have that analytically, you might know that, and other times you don't, especially if you're computing with something that's moving, a drop or whatever, you just have a discretization of it, you wouldn't have that. So what we did this was an important step in getting good estimates, was to do a good approximation of this gamma. So basically just using the discrete points on this panel, we build a Legendre interpolant that approximates gamma over the panel. And with this Legendre interpolant and some rather simple to compute initial guess, we can solve for this T0 using Newton's method and get the good, very efficiently, fast, and we can get a good approximation to T0. So if we look at this just for one panel still, and look at the errors, so this is something we're going to see quite a lot of. So the colors here are measured numerical errors. So this is what we actually get. And again, it's a logarithmic scale. So when you see blue here, that means like round off, right? And then the black contours are the error estimates. So here we look at the flat panels, which will be the simplest estimates. And here we look at the curved panels, which means we have to take a Z0 here, numerically find the T0 it corresponds to, and evaluate the estimate for it. So these are just two examples of different powers here. It's 1 there and 5 there. And then you see how they look. So now what we want to do is we want to put it together. We had this slide before. So here we have an error in the solution of Laplace equation. We looked at this zoomed in picture and we wanted to understand that. So now we're going to take that estimate that we have. So if we look at this one, this is what we had before. This was just our G, was mu. Now we do have an imaginary part that we can move outside. Mu is real. And so to show you, I'm going to do two different estimates. This is what comes from what I wrote before, just without the imaginary part. Now I'm also including an alternative, including the imaginary part. So this is the estimate for the Gauss-Legendre with this rho factor, and this is the decay that you recognize for the trapezoidal rule. And we are really, for the Gauss-Legendre, we are really going to, for the panel close to Z0, we're going to determine T0 by Newton's method. To include the density mu here, we're going to form a Legendre interpolant also for mu. You could also just do the max norm over the panel, actually, that works rather well. And we're going to add error contributions from the two closest panels. Then the rest has negligible. There's slightly different procedure for trapezoidal rule, and I'm going to get back to that. But if we now look at the errors that we get, or the results that we get, we found it when we first saw these, quite amazing. So we have here, the colors are measured errors again, and the black contours are error estimates. So if you look at the colors first, you can note that the Gauss-Legendre and the trapezoidal look a bit different. With the Gauss-Legendre, you can really see the panel structure, which of course you don't have with the trapezoidal rule. But you can also see, if we include the imaginary part, the estimate, which are these black lines, really follows even the wiggles of the actual errors. So we capture even these little wiggles. And if we then take instead, without the imaginary part, just the absolute value, we get an estimate that kind of, that bounds or convolute, it's like a smooth envelope of these wiggles. So these estimates were much better maybe than we would have expected. We have thrown out quite a lot of terms and still they are this good. And this is just to show you what happens, to get the feeling for what happens if I increase from n is equal to 16 to 32. Well, what happens then is that the error zone here will decrease. It will, it will get more accurate, closer to the curve. But at some point, you will still get these large errors, but you are making the error zone thinner. Basically, that is what's happening. Okay, so this was for the complex ones. So now I said we wanted to look at real valued layer potentials as well. So this is the prototype. If you have a real valued, or cartesian, as I also call them, layer potential. So we have some kernel and a density, and this is the kind of what sets the singularity. So we might have p half integer, like a half, or we might have it like 1 or 2. And so this is when we write it in parameterized form. So what we want, of course, to, oops, I think I skipped something there. We want to collect then all the smooth components here. We're going to collect into an F, and we're going to study the error of this integral. Okay. So what we're going to do is we're going to call this one, not with the p, but with the square. We're going to call that r squared. So that's our distance function on the bottom. And if we do that, we can call the integrand, we denote the integrand by theta sub p, and it will be on this form. And this is now the distance function. D is just to indicate here that it's 2 or 3, depending on the dimension. Okay, and we want to estimate the difference between the actual integral and the quadrature. So we're going to introduce now a T0 again, but it will be quite a little bit different than a pre-image. Instead, this time, since r squared is real, we're going to have a complex conjugate pair of roots, T0 and conjugate of T0. And we're going to say, those will be the ones where r squared is equal to 0. Okay, so this is how we use it. And then going about deriving the estimates for p integer, it is quite similar to before. Not that I've shown all the details, but it's the same idea with residue calculus. And we get the formula of the following kind, where this again will depend on the quadrature rule. And we have a so-called geometry factor that we have introduced, which depends on the parameterization and your evaluation point as well. And then for half integer p, then we have to work with branch cuts instead. We can't do residue calculus. And we get the more complicated form with this j here, which has an integral that follows the branch cut where this function appears. So here we had to work much harder. So first, just to say, the integer p is typical if you have a layer potential in 2D. But half integer p, meaning that you'd have 1 over r, for example, is typical in 3D. So we derive the estimates differently, residues, branch cuts, but actually, after all this hard work with the branch cuts, it turns out that if you just recognize that for positive integers, p minus 1 factorial is the same as the gamma function of p, you can actually write the estimates that we arrive at identically to each other. So we get only one form, which looks like this. So these are the estimates. I'm not sure exactly what to say about them. They're we recognize these things from before. The T0 is slightly different. It's the roots, not then we have a geometry factor, but we do recognize this kind of decay behavior that we have seen before. Okay. Now one can of course wonder then, if we would do this for a 2D curve, what is the relation to what we did before? And these details I'm not actually going to go into, but if we know what the complex estimate said, and if we look at the harmonic AA potential with real variables, and we kind of write out what things are, how the normal vector can be expressed, and what that means for the roots actually of r squared, then we can actually show that this estimate becomes exactly the same. So you cannot definitely relate the two to each other, but it's of course convenient to have it on both forms, depending on how you have your layer potential. Okay, so we have some results here then to look at. So we're looking at this curve. This is the curve going around. Oh, that's the curve, sorry. And then we wanted to create some test points so that we can look at the error at about the same magnitude. And we've used here that we know kind of how the error decays, which is easy for the trapezoidal rule. This funny shape kind of comes from the Bernstein ellipsis, trying to put points there. So we did this to be able to kind of collect results like this. So what does this say? Well, if we look here, for example, the Gauss-Legendre, we're taking the maximum error of 1,000 evaluation points, and we can see that the estimates follow the actual errors really well, down to where the actual errors flatten out due to numerical round-off. But until then, the estimate follows them well. The same for trapezoidal rule. And here, what we've done is that for each p, we have one color of the scattered points, and we measure the error in all these points. And then we have our error estimate here. And we can see that the error estimates that we have, these are for different p's. This is Gauss-Legendre, this is trapezoidal. We can see that they provide good approximate upper bounds of the quadrature error. And then they are on different levels, because the larger p you have, the more peaked your integrand will be. So the harder it is to resolve. So you're expecting a larger error. So we're not really working with the error here instead of affecting the error. We're just trying to estimate it. So we have some root finding here to look at. And what we do is that for the Gauss-Legendre panel, we're going to do this in the basis of Legendre polynomials as before. For the trapezoidal rule, the trigonometric polynomials will be natural, but it will get more costly since it's global, right? The trapezoidal rule is a global rule. We don't want to involve the whole curve in finding a root. So what we do then instead is that we do a local approximation. We do a Taylor expansion, a local approximation, to actually look at this, how well this comes out. And once we have an approximation, we can again use Newton's method. So this is just to show some kind of visual accuracy of this inverse mapping. So if we start with a grid like this and we map it to these points, and then we do approximate numerical mapping going back, just this local approximation. If we do a linear approximation, q is equal to 1, if it were perfect, we would get this picture back. Now, of course, we're not getting it back. And here it's a bit better. And for q is equal to 4, it's starting to look very good. And so if we think about what our estimates are, we really have our error estimates, which is one thing, how accurate they are, but we also have this T0 that we have to plug into the error estimates. So if we have an error in that T0, which we will get if we don't have a good approximate map, then we get the large deviation here, which is what we see for q is equal to 1. But for the higher ones, it follows really well. So looking at curves in 3D, we're moving up now. It's the same estimates. So then the layer potential, this is one example, the harmonic single layer potential, that's for Laplace equation. You'd have something like that. And we would, then this was our generic form. So we would have p is equal to 1/2, and that would be the f for actually evaluating this. And if you do that, again, we're going to use what I just said for the root finding. We're going to use local approximation of the trapezoidal rule, the whole panel, the Gauss-Legendre. And if we do that, we get these kind of error curves now. So now the curve is the red curve on this squished torus is what you see. And we're plotting again the same kind of contours that you've seen many times, but it's in an XY plane for a fixed Z that we're plotting it. So we get the good estimate here too, a good match of the contours. But now we're ready to take the big leap with what we have to go to layer potentials over 3D surfaces. And now we're going to have two variables. We're going to have a base interval, A1, and two across E2. So we'll have two variables, S and T. And again, we will write our layer potential, writing it out in the parameterized form. We will collect everything smooth in this F again. So that's F as a function of S and T. And we will study this one, okay? And so we have the integral, now double integral, we will denote IS, IT. We have a quadrature rule, which we will assume is a tensor product. So one in the S direction and one in the T direction. And when we look at the total error, the difference between the two, there should be three terms, this one, and a quadratic term, which we have neglected. But this term here is, it is really the error that we had before, let's say in the T direction, but then it needs to be integrated in the S direction. And then we have the opposite one as well, with S and T interchanged. So looking at that, well, we want this absolute value, but that means we can integrate the absolute value. And we have an estimate for the absolute value. This is the results we had before, because this is for a curve in 3D. So we have an estimate for that. And this, now I'm just writing this estimate so that I'm combining them and writing them. This is what we had for the trapezoidal rule. This is what we had for Gauss-Legendre. Now, the important difference here is that this T0 will depend on S. So before T0 was for one evaluation point X, T0 was just a point. Now it depends on X, it depends on S. So we need to think about that. So we need to evaluate this integral here. And if we would want to find T0 for several S, to find T0, we have this root finding procedure. Then we would need to do that several times for one evaluation point. And we don't really want to do that. This is just an estimate. We want it to be cheap to compute. We don't want it to be expensive. This is just something extra that we're doing. So instead, what we do is we find the closest grid point to X is a gamma star, and we call the parameters S star, T star for that point. And then we use root finding only once to determine T0 for that specific S star. And without going into any details, we use a local analytical expression then for how to write down T0 of S. And then we have to evaluate this integral, and we do that by numerical quadrature. So Gauss-Legendre, we just use the panel. For the trapezoidal rule, we use something special again to localize it. So we use a Gauss-Legendre quadrature as it's used. Okay, but anyway, so a semi-analytical expression for T0 of S, integrating this numerically. And then of course we have to repeat with S and T swapped. We have the two terms that we have to do. So how well does this work out? Well, we're going to look at this kind of a surface. This for the double layer potential now, the harmonic double layer potential, so for Laplace equation. This is a trapezoidal rule discretization. This is a Gauss-Legendre discretization. And these dots here are signifying, we're going to look at when we have evaluation points just scattered. And we're also going to look at when we have evaluation points on a plane cutting through the surface and see how it looks. It's harder to visualize in 3D. So if we do a scatter plot of, this is estimate versus error, that means that if the estimate was perfect, all the points would lie exactly on the red line. Well, they don't. So these black lines are like a factor of 10, 1/10 and 10. And we can see most of them lie there, but there is a deviation. So these are not as exact as the 2D rules, but they are still giving us a lot of information, but we realize we need a safety factor here. We can't say that they are precise, so we need a bit of a safety factor. If we instead look at cutting through with the plane, we see that we have a rather good correspondence here with the contours for the trapezoidal rule. For the Gauss-Legendre rule, we have a good correspondence. This is the most important region here where the error is starting to get large. in the area out here, which is far from the contour where the errors are at round off, we had some problems with the root finding procedure. So the contours are not good there, but this is the less important region. So we haven't really worked on fixing that. We could also evaluate these, if you want to have more information, to look at the toroidal shell. So we set the shell like this outside of the surface. And because this is squished torus, the closest distance will be very different. And we can plot the results with these two periodic variables over the shell. And if we do so, we see the following result. So this is trapezoidal rule again, and this is Gauss-Legendre. And so we see how we capture quite well these different shapes of the colored field. It's not as exact, certainly, as in 2D for Laplace, but it's still giving us a lot of information here. So with that, I'd like to summarize. So I have introduced the theoretical and the numerical framework for estimating quadrature errors in these nearly singular layer potentials. And why do I say a theoretical and a numerical framework? Well, we've done the theoretical work in deriving the error estimates, but then we have this T0, for example, which we don't typically know analytically. So we have to have a numerical framework for how to actually find that to a good approximation to be able to evaluate our error estimates. And also for the 3D case, to actually be able to do the outer integral, we also use numerical integration of the estimate for the curve. So we have looked at, we started complex, we went to real valued curves in 2D and 3D, and then to surfaces. And when it comes to the performance, I would say that for curves, the estimates are in some cases remarkably precise, even though we've thrown away some curves. But for surfaces, we typically estimate the errors to within like 1 order of magnitude. We have a lot of information about the structure, but we're definitely not perfect there. So for some future work, in 2D, we used our estimates to actually build the adaptive quadrature method. Also, not just to decide when the regular quadrature method would switch to a special one, but also to actually set parameters in that method. And we'd like to do something similar for the 3D case. And we also we're doing simulations with 3D drops where we have a discretization with spherical harmonics, meaning that you have two angles as parameters. And it's like if you discretize a sphere, right, where you get this north pole. And we want to look at how to actually extend their estimates to these type of parameterizations. So with that, I thank you for your attention, and I will end there.